this. I'm sharing my screen. That's great. All right. Oh, before we jump into chapter 3, I fixed it on Moodle. So now it says 17th, which is true. Because that's what we said we would do. We're going to start chapter 3 today, which is not on test 1. So just need more time to work through it. But I did post a practice test with solutions. I had good intentions. I was going to kind of boost it a little bit. But the only thing that I was really going to do was add a regression question, and that's it. So I'm just going to tell you what to add, and then you can work through that. So these I have stolen from your assignments and those review problems. They just look different on paper, right? And so I just want you to see what they look like when they're on paper, and then it'll look something like this on the test. Okay. Blah, 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 blah. Where is it? This one here. So after 16, which is a regression question, I want to also add Excel output with the line and the R squared. And then I get you to kind of interpret that, because we did spend a whole day on that. So I get to test it. Okay. And so that was section 2.4, I want to say. Okay. And so I'll add another question there. But besides that, you know how to do all these things now. I also posted a test 1 formula sheet, just so you know what you'll have. So I'll give you this, and it is just, I just decided to steal the ones that we had exactly in class, because then you've seen them before. They're a little bit verbose, right? So kind of wordy, but I thought, no harm. So this is what you will have and all you will have. So anything else you need to have up here. Okay. For Tuesday, next week, I do want to start 3.2, but if you do have questions about the practice test, then we'll just kind of take those, right? Because chapter 3 is not on the test, and so I'm fine kind of bumping it if you have questions. And so that should say kind of test 1 review, in the way that if you bring me questions to work through together, then we can do that. Okay? But otherwise, I think you have what you need. Any questions about that or the test? So, no questions. Chapter 3, big day. I'll even say it here, not on test 1. Oh, wow. It's so laggy. It's crazy. That is very annoying. All right. In section 3.1, we're just going to talk about what a power function is and what a polynomial is, and some properties of power functions and polynomial functions. And so we'll start with a power function. And a power function is any function that can be written in the form of f of x is x to the power of p, and so makes it a power function. So the exponent p is a number. The base is the variable. Now, what we're going to find is that all of these toolkit functions are power functions. So let's have a look. All the toolkit functions Oh. Is it laggy on your end too? Our power functions, I can't tell. Okay. So if we have to rewrite all these as power functions, well, f of x is equal to 2, for example. Well, f of x is equal to 2 is the same thing as 2 to the power of 1. Now that's not really a power function because the variable is just, it's not a variable, it's just a constant 2, right? And so I wouldn't really call it a power function, but we could rewrite it as a power, 2 to the power of 1. You could do the same thing for the next one, f of x is equal to x. Right, we're pretty comfortable with these lines now, right? We've seen a lot of lines, we know how to work with lines. And so f of x is equal to x. Well, that's the same thing as saying x to the power of 1. Kind of boring, but we can. Now we get into some true power functions, right? The interesting ones. The quadratic x squared. Well, I have x to the power of 2. So f of x is equal to x squared. I have p is equal to 2. Right, from that power function definition, x to the power of p. Right. Same thing with the quadratic, x to the power of 3. Well, if f of x is x to the power of 3, then p must be 3. Square root is a power function because I can rewrite the square root as f of x is the square root of x, but that's the same as x to the power of 1, oh, sorry, not 1 over n, 1/2. So I'll make a note here. Note, the nth root of x is the same as x to the 1 over n. That's a fact. So if you're trying to take, the 14th root of something, then on your calculator, what would you do? You would take whatever you want to take the 14th root of to the power of 1 over 14, right? So for example, if you want to take the 14th root of 32, I don't know, that's the same as 32 to the power of 1 over 14. So that's how you would do it on your calculator. Which means that we can rewrite any root as a power. Right? So therefore, all roots are power functions. So then we know what the third root of x is going to look like, right? F of x is the third root of x is the same thing as x to the power of 1 over 3. So p is 1 over 3. I guess I didn't write that. P is 1/2. I'll sneak that in there. So p is 1/3. I'll tell you that the reciprocals can also be written as power functions, right? And if we have f of x is equal to 1 over x, right? I can rewrite this x in the denominator as a power of -1. Right? And so if f of x is 1 over x, that's going to be the same as x to the -1. One, because this is technically x to the power of 1 in the denominator.
Sound's going to be up in a second.
Oh, thanks. Save me a trip. So 1 over x squared then, if I have to rewrite it as a power, f of x, if it's 1 over x squared, if I need to, I think of it as floating that x squared up to the numerator, then I negate the power. So then I get x to the -2 is the same. Okay, so really what we're saying is that another note is that 1 over x to the power of n, so we just use a generic n, is the same as x to the -n. Right. Well, and I guess I was writing the p's. So in this case, p is -1, and in this case, p is -2, but you can rewrite any power in the denominator as a negative power in the numerator, which is really useful if you want to move things around, right? Kind of move x's from the denominator up to the numerator. Float them to the top is how I think of it. Okay. So all of those functions we can rewrite as power functions. Okay, so that's kind of cool. Any questions so far? Here's some examples of what x squared. So x squared is this purple line, and x to the 4th is the green line, and x to the 6th is the blue line. So what's happening as you increase your powers, right? They're kind of getting tighter and tighter together. But also notice that all the even powers, x squared, x to the 4th, x to the 6th, right? That's kind of indicating that, okay, it looks like all the even powers have this same general shape, right? And so if we know what the general shape of x squared is, which we do, right, this parabola, then we know in general how all the even powers work. Okay? And so the shape of all even powers will be similar to x to the power of 2, right, which we know. So if we know in general what anything x to the power of an even power looks like, then that's really useful, right? We've seen it before where, okay, if I can kind of visualize what the graph looks like, not necessarily draw it, but kind of understand what a reasonable graph looks like, then I can figure out what some reasonable answers are, right? And so it kind of helps us find our answers. What about odd powers? So we start here at x to the power of 3 is the purple line, and then x to the power of 5 is the green line, and x to the power of 7 is the blue line. And it does kind of the same thing. It just kind of tightens up as you increase your power. But the general shape of odd powers is this kind of, I want to say S shape. That's not an S at all. Pardon?
Chair.
Oh, a chair.
Do they eventually like?
I guess if you do like this. Yeah, I'm like, huh, I didn't see it. It was too early for me.
Let's see who's more.
Like a
Once you
chair.
go higher, do they end up like turning into like almost a figure eight?
No, they just always, so they're always kind of going outwards.
Well, I know, but like it keeps like elongating this way too, right? So, like,
Yeah, well, they kind of like sit on the x-axis. So they're kind of getting closer and closer. They never are flat, but they kind of smush down on the x-axis.
So I think he was meaning, I think he meant like the top or the bottom, do they like slowly separate like as they go on?
They do, but it goes slower as you increase your powers. So here, just like this purple one, you can kind of see that it's going to take off. The other ones behave the same way, but at a large or a higher angle, I guess. But they all behave that same way. And they never kind of curl back on themselves. They're always moving out. Okay. So all odd powers, I almost said even. All odd powers behave like x to the power of 3. So knowing what x squared looks like and what x to the power of 3 looks like, then we know the general behavior. And what we were talking about was that that end behavior, that tail behavior. And so what we want is we want to be able to talk about the behavior. Let's go back up here. The behavior as x goes to infinity. So as x moves out towards infinity, and so this is as x moves to infinity. And then we're going to talk about the behavior as x moves to negative infinity. And we're going to call that the end behavior. In fact, I'm going to give myself another line here. The end behavior as x moves to infinity, f of x does what? F of x also goes to infinity. So f of x goes to positive infinity. What about as x goes to negative infinity? F of x, so the output goes to positive infinity again. So really what we're saying is that all even powers have the same end behavior. So I'll say same end behavior. I'll add the same here, same end behavior. Oops. And the end behavior for these guys as x goes to positive infinity and as x goes to negative infinity, f of x goes to, so as x goes to positive infinity, then f of x is going to go to positive infinity. But as f of x goes to negative infinity, for the first time ever that we've seen, f of x is going to go to negative infinity. Oops, that's not infinity. Okay. So let's do an example. I feel like A is actually harder than B. Should we do B first? I'll do this. Change this to B and change this to A. Why is this first one harder?
Because it has a negative sign.
Yeah, I guess we could just do it. Should we just do it? We know how to do it?
I think so.
I think so too. All right. So we want to describe the long run behavior or the end behavior of each function as x goes to infinity and as x goes to negative infinity. All right. A is f of x is equal to negative 2x squared. First thing we know is that, okay, this general shape looks like this, right? So even with the 2 multiplying, that's not really going to affect us, besides kind of how tight or how wide it is, right? But the negative is the troublemaker, because the negative does what? It flips it over the x-axis. So now as x goes to positive infinity, f of x is going to negative infinity. And as x goes to negative infinity, again, f of x is going to negative infinity. As x goes to infinity, f of x is going to negative infinity. And as x goes to negative infinity, f of x again is going to negative infinity. Thanks. I have g of x is 3x to the power of 3. Oops, I have a screen. I have a power of 3. Now, a positive coefficient isn't going to do anything, right? In fact, we can have a look at Desmos if we want to. Maybe. If we do x to the power of 3 versus, what was it, 3x to the power of 3? Right? It just kind of tightens things up, but the general shape stays the same. Let's see if I can bring that in here. Ah. So here, let's see, the coefficient the coefficient does not, so the positive coefficient, I'll add that. The positive coefficient does not affect the end behavior, right? Does not affect the end behavior. Makes it move faster, but move faster towards the end behavior. So as x goes to infinity, then f of x is going to infinity again.
So we could say this doesn't change.
That's true. Yeah, you could say that. I only said end behavior because we're talking about the end behavior. But yeah, I'm fine with that. As x goes to negative infinity, f of x is also going to negative infinity. Still, same as x to the power of 3. Yeah. So we've been talking about, so the long run behavior, I've been calling it end behavior or end behavior. It doesn't matter. But when we talk about how f of x behaves as x is going to negative infinity or positive infinity, then we're talking about the long run behavior of the function. Okay. Any questions before we do a word problem? Not so much an example, but a word problem. Get warmed up here. Power functions. We use power functions often, right? And so here, we're just gonna do a little word problem, get warmed up, and see how we solve these things. So an oil pipeline bursts in the Gulf of Mexico, causing an oil slick in a roughly circular shape. The slick is currently 24 miles in radius, but that radius is increasing by 8 miles each week. If we wanted to write a formula for the area covered by the oil slick, the area of a circle, we remember maybe the area of a circle pi r squared. So what we could do is we could use function compositions to figure out an overall function of pi r squared. Why is it a function composition? Because the first function for the radius depends on how many weeks have passed, right? And so really, the area is a function of the radius, but r is a function of w, where w is the number of weeks. While I'm thinking of it, there was a mumba jumba question in the 2.3. Let me go there. In the 2.3 problems. And I want to emphasize that that is not something that I'm going to test you on. where is it? Probably last week. I posted it in the general notes, but also in this week, just so you'd have them. So the solutions, the first one is fine. Second one is fine. Third one is fine. And then I made a note. I do so we have all the knowledge that we need to solve this problem. And so I encourage you to try it. It is not something that I would expect you to do. The only reason I'm thinking of it now is because it's similar to this oil spill, right, which is also a circle, right? And so, so I've got the solutions here, but it took me, I don't know, 3, 4.5 pages. But I redid it with exact values, and what you find is that they're very different, and so, or relatively different, and so I guess only 3 pages. Yeah, so we will use the circle. In fact, how do I grab that? Now we just know. Okay. Let's draw it out. So we've got the initial oil slick. The slick is currently 24 miles in radius. So to start, the radius is 24. Then the radius is increasing by 8 miles each week. So for each additional week, we add 8 miles. Oops. Oops. And so on. This is a linear function, right? The radius is increasing, so we start off at 24, and then it's going to increase by 8 each week. Okay? And so what we have is the radius in terms of the week is going to be 24 plus 8 times W. Presumably, that's not how oil slicks work. I don't think that they are continuously expanding by the same amount each week, but that's what we're assuming, right? That's what we're told. And so, although I guess I don't actually know how oil slicks work. So this is all I've got. Might be worth a Google. But I don't think it's linear. But in this case, it is. So now I have a function for the radius, right? Which I can then use in my area. So to find a function we can use the function for the radius, oops, in our area function. But really, what are we doing? The area of the radius, but the radius is a function of the weeks. So this here is a function composition, which is why we had to work through those, because we're going to be stuffing functions into other functions. pi r squared. Pi is just pi. And the function of r, I can replace it with 24 plus 8w. We should be thinking about things like the domain, but the domain of a straight line is just all real numbers, so that's fine. And then same thing with pi r squared. And it's kind of beyond what I expect you to do. Oh, I forgot the square. What I'm gonna do is I'm gonna expand this so we can see. And when I expand, I have to do it slowly. 24 plus 8w. What do you guys call it? Feeding the chickens? That's how I do it. I always have to do it. Whenever I have a square, I just write it out side by side. And 24 times 24 is 576. I'll keep the pi outside. 576 and then 24 times 8 plus 192w plus 192w plus, is it 64? 64w squared. Let me just squeak that down. 192 plus 192, I can collect those like terms and I can get pi times. Now, what I'm gonna do and encourage you to do is I'm gonna rewrite these with the powers in descending order. So I rewrite the w squared to be at the front. Okay, the leading term is what it's called. And so I'm going to rearrange this to say 64w squared followed by the w term, then followed by the constant. Now 192w plus 192w is 384w, and then plus 576. We can multiply that pi inside to get 64 pi w squared plus 384 pi w plus 576 pi. Notice now, right, I've got some coefficient here and some coefficient on the w and some coefficient which is just on its own a constant. And so what we're going to say right here, I've got some power functions, right? And when I've joined up power functions, I get what's called a polynomial. This is a polynomial. Guess I wrote bigger this time than last time. But what we can do then is we can plug in the number of weeks that have passed to find, well, we can find the radius, but using this function, right, we can find the area of the oil spill after W weeks. That's kind of cool. But we were building a polynomial. Any questions about that one before we talk about some more terminology, not really properties of polynomials, but terminology? Okay. So in general, a polynomial is any function that you can write as a subscript 0 plus a subscript 1 times x, a 2x squared, all the way up to a n x n. And notice here that a subscript 0 is really times x to the power of 0, but x to the power of 0 is 1. So we don't write it, right? So we've got some coefficient and some x. In fact, each of the a subscript I constants are called coefficients, and they can be positive, negative, they can be 0, making that term go away. They can be whole numbers, they can be decimals, they can be fractions, they can even involve pi, like we saw here. So here we have a coefficient on our squared term of 64 pi. Okay? So these are all the coefficients. Wait. A term of the polynomial is any one piece of the sum. So for any ai, xi, and the individual term is a power function, right? And so we add up all these power functions to get a polynomial, but we're going to call each of these a term, right? Now here's where it gets important. The degree of the polynomial is the highest power of the variable that's in this polynomial. So for us, we had w squared, so that's the degree must be 2. I'm going to say that these properties, I guess it's right there. I was going to write that out, but the reason we wrote the powers in descending order is because now we're going to be talking about the degree of the polynomial, which in this case is 2. Yeah. Maybe I'll write that down. Degree is 2, the highest power of the variable, which is w in this case. The leading term is the term, so the chunk of things that contains the highest power. And so the leading term in this case is 64 pi w squared. Right? Each of these are terms, right? But the leading term is 64 pi w squared. And then the leading coefficient is the coefficient of the leading term. And so the leading coefficient is 64 pi. So here, oops, because of this definition of the leading term, and what we're going to do is we're going to be relying on the leading term to figure out the end behavior of this graph. And so we're going to be using the leading term quite a bit. And so for that reason, we often rewrite them as the highest power first and then decreasing. The only reason we didn't to begin with is to show that it starts at 0 and then it can increase all the way up to n, right? But they all behave the same way. But in general, a polynomial is going to be written like this with the decreasing powers. If we have to find the degree, the leading term, and the leading coefficient for each of these, I'll say degree, leading term, and the leading coefficient and maybe I'll copy that for the next one. First thing you want to do is, so this is a polynomial. The terms, we can also call them nomials. And so poly meaning multiple nomials, multiple terms. And so the degree of this thing, first thing you want to do is make sure that you've written them or that they are written with decreasing powers. In this case, the degree, the highest power is 5. Here. Should use some other color, I think. The degree is 5. The leading term is that entire block, right, with the highest power in it. So the leading term is negative 3x to the power of 5. Making the leading coefficient negative 3. If you had to rewrite this, starting at x to the power of 5, with all the x's in there, what would that look like? We can rewrite or f of x is negative 3x to the 5. There is no x to the power of 4, which means what? It means that it's still in there, but the coefficient of x to the power of 4 must be 0. So you can rewrite this as 0 times x to the power of 4. There is no x to the power of 3, so same thing, times 0 or plus 0 times x to the power of 3. There is an x to the power of 2, so minus 3x to the power of 2. There is no x term, and so I have plus 0x. I'll do to the power of 1 just to emphasize that we are still decreasing the powers. And then plus 1, uh-oh, just not enough room here, hang on. Oh boy, now I've done it. Copy. No, no, no. I wrote on the thing. And now it's hanging together. Okay, well, plus 1 times x to the power of 0. Just have to be careful. X to the power of 0, right? Where x to the power of 0, anything to the power of 0 is 1. If you had negative powers, you would write them after the x to the power of 0, right? We're not going to deal with that, but you would. Nice. So this, writing it out as the full polynomial will come in handy later on. And so, but for now, we're just going to ignore any coefficients of 0, right? But just know that you could put them in there if you need them. Yeah. But the next one, this one is not in order. So that's the first thing that you want to look at, right? Kind of sneaky. In order, g of x, you could grab the degree and the leading term and the leading coefficient without rewriting them if you want to. but I always like to have them rewritten just so I can not think so much. In order, it would be 4x to the power of 4 plus x to the power of 3 plus 3. Now, I see that my degree is 4. My leading term is 4x to the 4. And my leading coefficient is positive 4. As we've seen before, right, that leading coefficient matters, right, because if it's negative, like it was in the first case, right, then it's going to flip on the x-axis. You have to kind of revolve around the x-axis. So what we're going to have, this long run behavior of polynomials. So for any polynomial, the long run behavior is going to match the long run behavior of the leading term. So that's kind of neat. So if I can figure out what the leading term is, and if I can know what that behavior is, which we do already, right? Because all even powers behave like x squared and all odd powers behave like x to the 3. And we might be flipping around the x-axis and things like that. But besides that, we know how all these behave. And so what we're going to see is that the long run behavior is after the leading term. Okay. First thing you want to do, right, if you have to describe the long run behavior of each of these, is just make sure that you've got your powers decreasing. So I'm going to check both of them right now so I don't need to think about it again. 3x squared x, okay, looks good. X to the 3x squared, okay, both of these are in order. So then, looking at this first term, the leading term, I have degree 2. Let's use so the degree 2 tells me that it looks something like this. I have a positive coefficient 3, which means that the general behavior is just that of x squared. Okay. Now, what this x does, this minus 6x, is it might change things in the middle. So now we're only talking about the end behavior. Okay. In fact, let's see what Desmos does. 3x squared, can I do it side by side? 3x squared minus 6x plus 1. Didn't really do anything crazy. But if I graph the next one, no, it'll give it away. I want it to be a surprise. Not really. So for this one, as x goes to infinity and as x goes to negative infinity, f of x is going to behave like x squared. And so f of x is going to go to positive infinity, and then f of x is going to go to positive infinity again as x goes to negative infinity. B is kind of the tricky one, I think. We make a note of the negative coefficient. Okay. And so what we have is we have degree 3, which we said looks like a chair, sort of. But then the negative is going to flip it around the x-axis, right? And so this turns up this way and then down that way. So now this long run behavior, as x goes to infinity and as x goes to negative infinity, g of x is going to go to, so as x goes to positive infinity, so now we're on the pink line. As x goes to positive infinity, g of x goes to negative infinity. And as x goes to negative infinity, g of x is going to go to positive infinity. Really, what it's going to look like is we know what it looks like here, and we think it maybe looks something like that in the middle, but we're only talking about the end behavior, right? Not that middle behavior. Let's see if when we graph this, if we get some action in the middle to show it. I don't actually know, so I'll be as surprised as you are. Negative 2x to the power of 3, step it down, okay. Plus 4x squared. Hey, finally, a little bit of action here. I'll screenshot this. Now, we're not expected to know yet what that middle activity is. All we're expected to know is the end behavior. Right, so here, we know the end behavior of this thing. And there's some activity in the middle, but that's okay. We're not there yet. Well, so if I give you a polynomial, you can tell me what the long run behavior is going to look like, right? As x goes to negative infinity and as x goes to positive infinity. What if I give you something like this? Rude. We don't have to expand this. This would expand into some big polynomial, right? We only need the leading term, right? And so here, oops. We only need the leading term to determine the long run behavior. Bless you. So what's the leading term going to be? If I have, I'll just rewrite it out so I have it. H of x is negative 2 times x minus 3 times x plus 4. And then I have x minus 1 squared, but I'm just going to write that as x minus 1 times x minus 1, and then I'll have kind of a clear view of what's happening. We know if you were to expand this out, right, you would get -2 times x times x, x times x times x, and x times x times x times x. Maybe I said one too many. I don't know. Got carried away. But the leading term here would be -2 x times x times x times x. So x to the power of 4. Pardon? Did I miss one?
The last part is the x minus 1 square.
Oh, yeah, so I wrote it out like the, oops, sorry. I was like, did I forget to? Because that's what I was worried about. I was going to forget. No, so I wrote it out as, so if you can see that it's squared, cool. I never can. And so I need to write them both out. But good. Okay, phew. So I get a leading term of -2 x to the 4th. All those other x's are going to be less than x to the 4. Right? Plus ba 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 ba. It doesn't actually matter. X to the 4 behaves like x squared, but what does this thing look like? We have a negative coefficient, which means that it's going to look like this, right? With maybe some activity in the middle there. It's not what we care about. For now, we only care about as x goes to -infinity, h of x is going to -infinity. And as x goes to +infinity, h of x is still going to -infinity, right? End behavior, or the long run behavior. So that's kind of cool. Figure out what it looks like overall. Now for the short run behavior, uh-oh. We just drew it like a squiggle here. The short run behavior is all this activity. So the short run behavior are things like vertical and horizontal intercepts, where the graph changes direction. And the first thing we're going to talk about is the horizontal intercepts are also called zeros or roots of the function. Right? Graphically, if we have some function, let's see, maybe like this, think. That's some function. Then these points here are the horizontal intercepts. Right, so here we have horizontal intercepts or roots or zeros. Oops. You might have called them roots or zeros before. We also have a vertical intercept we also have what? Places where the graph changes direction, right? And so here we can draw it kind of close to, so here changes direction, here it changes direction, and here it changes direction. Change of direction. Right here, remember from chapter 1, right? This is a decreasing function, and then it changes to increasing, and then it's increasing up until this point, and then it's decreasing, and then it's increasing, and so it's changing direction. Throws me off. So this is all part of the short run behavior. So how do we know what these things look like? We have to find the horizontal and the vertical intercepts. Let's go back to our graph to figure out what that means for us. These horizontal intercepts are what? They're the values of x where y is 0, right? And so here, oops, the values of x that make the function 0, right? The output 0, that make the function 0. Or if you prefer, wherever f of x is equal to 0, right? And that's why they're called zeros. Often we call them roots. I don't know why, though. Why do we call them roots? I don't know. I suspect it's from the quadratic, but who am I to say? The vertical intercept we know is where x is 0. So it's the output where x is 0. The vertical intercept is the output when x is 0, which is really just f of 0. So you evaluate the function at 0. Because it's a function, you can only have one vertical intercept, right? Because to determine if we have a function, you use the vertical line test, and it's only allowed to pass through the function at one point, right? And so at x equals 0 and any other x, it's only allowed to pass through one point of the graph. So you'll only ever have one vertical intercept. It's the horizontal intercepts that you can have many of. Okay, so knowing that, we can find the horizontal, which we said was wherever f of x, or I guess it's called g of x in this case, so I'll be consistent. G of x is equal to 0. And the vertical intercepts, which is when at g of 0. This one is nice because it's been factored. And so what you're going to find, even though we tried to expand the other function, which was factored like this in a similar way, right? To find the leading term, to find the overall behavior. But for finding the horizontal intercepts especially, the factored version is going to be a lot easier. Okay? And so this is the factored version, a factored polynomial. And it makes our job easier. Why? If we're focusing on where g of x is equal to 0, right, the horizontal intercepts, if I have g of x is 2 times x minus 1 times x plus 3 times x minus 2, iPad's driving me batty. If I need to force this to be 0, I see that 2 times 0 times something, well, as soon as I'm multiplying by 0, it all goes to 0. Right, so what I can do is I can force this to be 0. That's going to be 0 if x is 1. Right? At x equals 1. We can do the same thing for the next block, right? I'll say or, and maybe I'll copy this so I don't have to. Notice that they're all being multiplied. All right, so as soon as I throw a 0 in there or an x that makes one of these 0, right, this is going to be 0 at x equal to -3. And you can set it up, x plus 3 is equal to 0 and solve for x, but you can also just kind of look at it and see what value would turn that thing into 0. Or oops. This last one, my other option is this is going to be 0 at x is equal to 2. Any one of those x's is going to force the output to be 0, which means that I have horizontal intercepts at x equals 1, or let's start at -3, 1, and then 2. So therefore, we have horizontal intercepts at x equals -3, 1, and 2. What about the vertical intercept? Vertical intercept is an easy one after we've found all the horizontal intercepts, right? I just plug in x equals 0 into g, and so I get, and I want to just double check here. Okay, I'm gonna bump these to the next page because I want to, or maybe it won't let me. I kind of smushed them. But I do want to work more on this one. So then the vertical intercepts, oh, come on. I'm trying to scroll, but it's not doing anything. The vertical intercepts is at g of 0, which if I bring down my g function g of 0 is 2 times 0 minus 1 times 0 plus 3 times 0 minus 2. Two times negative 1 times 3 times negative 2. Be careful, Emily. 2 times negative 1 times 3 times negative 2. I get 12. At x equals 0. What about the long run behavior? I'm adding it for completeness. The long run behavior of something like this, well, 2 is positive, and then we're going to have x times x times x, right? And so here, the leading term is going to be, 2x to the power of 3 plus something else. X to the power of 3, we know what that looks like. It's got a positive coefficient, and so it is just going to behave like the chair. So then, what do we know about this long run behavior? It's going to behave like this. Notice how I'm not drawing the middle yet. What else do I know? I know that it passed through the vertical at 12. We also know the horizontal intercepts, -3, 1, and 2. So I'll throw those on here. Maybe make this -3. Not very good, it got squished, but I'm trying to keep it on one page. -3, 1, and 2. I'd say it's relatively obvious what has to happen to get from this end behavior to pass through here to pass through here, right? It has to go in this kind of this arc like this. I'm just guessing though, so I'll do kind of dotted lines like that. Then I know that I have to go through 2, right? And I also have to go through 1, and I can't cross the axis more than that, right? And so a reasonable guess would be that it maybe looks something like this. Reasonable guess. I don't know how low it goes or anything like that. I just have a general idea. Having the general idea lets us answer questions like, where is this function positive? That's going to be on an interval, right? It should be positive between -3 and 1, and then from 2 to infinity, right? Where is it above the x-axis? Where is it negative? Well, from -infinity to -3, and then between 1 and 2, right? Reasonably. Let's use Desmos to see what this thing actually looks like. Two times x minus 1 bracket x plus 3 bracket x minus 2 and bracket. Look at us go. try to get some points on there. Maybe not that one. Yeah. Eek. There. So that's kind of cool, I think, being able to know what this function reasonably looks like. Like I said, we don't really care about, well, not yet anyways. We don't really need to know how far down it goes here, right? But just knowing that it dips down is enough for us. Nice. Any questions about that one? Okay. Got a fresh page here, so I'll just scoot it to the top. Okay. Intercepts and turning points, emphasis on the turning points. A polynomial of degree n will have at most n horizontal intercepts. Yeah. An odd degree polynomial will always have at least one, because we know what the chair looks like, and it has to pass through the x-intercept at some point, or the x-axis some point. It's going to have at most n minus 1 turning points. Turning points are those points where it goes from positive to negative. So what if we have something like this? Try to make it bigger. We'll do them down below. So if we have the graph, what's the least possible degree of these graphs, right? So the degree is the leading term. Okay. First thing we know is that, okay, I know this end behavior. This end behavior to me looks like x to the power of 3, right? So that's a good starting point, right? And so the lowest degree is 3, question mark. I'm gonna have to confirm using those rules for the turning points. So a polynomial of degree 3, if we replace these with 3, will have at most 3 horizontal intercepts. And so now we're going to count the intercepts. I've got 1, 2, 3. Okay, degree 3 is still working. Yeah. And it's going to have at most n minus 1 turning points. So we need to figure out, okay, how many turning points do I have? Well, here I'm increasing, and then I turn and I decrease, and then I turn and then I'm increasing. So I've got 2 turning points. Two turning points. I can have at most 3 minus 1 turning points. And so the least degree possible is 3. Oops. Because the rule says that we can have at most n minus 1. Now we're letting n be 3 to c, right? So 3 minus 1 turning points. So it's allowed to have 2 turning points at most.
Then why is it 3?
So what we do is you start with the smallest possible degree, and then you bump it up if you don't meet all the criteria. So in this and from this end behavior, we're kind of working backwards, right? From this end behavior, we start with, okay, the smallest possible degree I could have is 3. And then if n is 3, right, if the degree is 3, then we can have at most 3 horizontal intercepts. And we have 3, so that still qualifies. And then we're allowed to have at most 3 minus 1 turning points, so 2 turning points, which is what we have. I think this one might be better. Starting with the end behavior, the smallest possible degree I can have is 2, right? And so from the end behavior, but notice how I write it as degree equals 2 question mark? And then I might need to bump it up if it doesn't meet all the criteria. I'm allowed to have at most 2 horizontal intercepts in that case. In this case, I do have 2 horizontal intercepts, so that criteria is met. So it could still be 2. The problem is when I hit the at most n minus 1 turning points, I see that, okay, I have 1, 2, 3 turning points. Three turning points. But we're allowed, at most n minus 1 turning points. So if n minus 1 is equal to 3, then n must be 4, is my lowest possible degree. So the lowest possible degree is 4. It still meets the other criteria, right? It has the shape of x squared. That's why we started at degree 2, right? Degree 4 has the same shape. And we have at most 4 horizontal intercepts. We only have 2, but that satisfies the criteria. And at most 4 minus 1 turning points, 3 turning points. And so that's how we get to our lowest possible degree of 4. So that's kind of sneaky, working backwards in a way. Okay. I think that's all I have. Any questions? No. Okay, so like I said, we'll keep working on chapter 3 next day, but if you do have questions that you want to work through as a group or kind of have me go through in class on Tuesday, then bring those. Otherwise, we'll just pick up in section 3.2. I hope you have a wonderful long weekend and see you on Tuesday.